Next-Gen Tech in Minutes by Lena Corvin. Introduction. Computing in the 21st Century. We live in an era defined by the rapid evolution of computing. From the smartphones in our pockets to the massive data centers powering artificial intelligence, computing technology touches every aspect of modern life. Yet, behind the familiar devices and applications lies a vast and constantly shifting landscape of research, experimentation, and discovery, an arena where hardware, software, algorithms, and systems are being reimagined from the ground up. This book is a journey into that frontier, a guide to understanding the cutting-edge developments that are shaping the future of computing. Computing has come a long way since the first electronic computers of the mid-20th century. Those early machines, enormous by today's standards, were capable of only basic calculations, yet they laid the foundations for an entire technological revolution. Over the decades, advances in transistor technology, processor design, and memory systems have made it possible to pack astonishing computational power into devices that fit in the palm of your hand. Software innovations, from programming languages to sophisticated operating systems, have harnessed this hardware to perform increasingly complex tasks, while networks have connected computers across the globe, enabling a new era of communication, commerce, and collaboration. Today, we are witnessing the rise of computing paradigms that were once considered purely theoretical. Quantum computers promise to tackle problems that classical computers cannot efficiently solve. Neuromorphic systems mimic the human brain to achieve energy-efficient artificial intelligence. Edge computing brings sophisticated processing closer to where data is generated, reducing latency and unlocking real-time applications. Even the hardware itself is undergoing radical reinvention, with optical processors, 3D, stacked chips, and novel memory technologies pushing the boundaries of speed, efficiency, and miniaturization. But these developments are not just incremental improvements, they represent a fundamental shift in how we think about computation. Researchers and engineers are no longer merely trying to make computers faster. They are rethinking what computation can do, how it interacts with humans, and how it integrates with our physical and social world. From sustainable computing that minimizes environmental impact to privacy-preserving techniques that protect sensitive data, the next generation of computing is being designed with both capability and responsibility in mind. This book seeks to capture this moment in computing history. Each chapter delves into a specific domain of research, from next-generation hardware and high-performance systems to artificial intelligence, quantum computing, and emerging interfaces. Rather than presenting a dry catalog of technologies, the book explores the underlying principles, the key innovations, and the ongoing challenges that researchers face. It also considers the broader implications, ethical, societal, and economic, of these breakthroughs, recognizing that computing is not just a technical endeavor, but a profoundly human one. Whether you are a researcher, a student, an engineer, or simply a curious reader, this book provides a window into the rapidly evolving world of computing. It invites you to understand not only the technologies themselves, but also the vision and creativity driving them. As we explore these frontiers, it becomes clear that computing is not merely a tool. It is a canvas upon which humanity is painting its future. In the chapters that follow, we will journey through the cutting edge of hardware and software, traverse the realms of artificial intelligence and quantum mechanics, and glimpse the speculative technologies that may define the next decades. The goal is not merely to inform, but to inspire, to show that the future of computing is a living, dynamic field where imagination, innovation, and intellect converge. Chapter 1. Next-Generation Hardware. At the foundation of every computational breakthrough lies hardware, the physical layer that turns theoretical algorithms into tangible results. While software often receives the spotlight in discussions about innovation, it is the evolution of hardware that sets the pace for what is possible. The last decade has seen an unprecedented surge in research aimed at redefining the capabilities of processors, memory, and integrated systems. This chapter explores these developments, examining how next-generation hardware is shaping the future of computing. 1.1 The Processor Revolution. Central processing units, CPUs, have long been the beating heart of computers, but today's landscape is far more diverse. Traditional CPUs, optimized for sequential processing, are increasingly complemented by specialized processors designed for parallelism and high-throughput tasks. Graphics processing units, GPUs, originally engineered for rendering images, now power artificial intelligence, scientific simulations, and data-intensive applications. Similarly, tensor processing units, TPUs, and other AI accelerators are pushing the boundaries of machine learning performance, allowing neural networks to scale to sizes that were unimaginable a few years ago. Emerging architectures like RISC-V and new ARM designs are also transforming the industry. Open-source instruction sets like RISC-V allow researchers and companies to innovate freely, creating custom processors tailored for specific workloads. These developments signal a shift away from the one-size-fits-all approach toward a landscape where hardware is increasingly co-designed with software for maximum efficiency. 1.2 Beyond silicon, new materials and designs. Moore's law, the idea that transistor density doubles approximately every 2 years, has driven computing innovation for decades. Yet as silicon approaches physical limits, researchers are exploring alternative materials and architectures. Gallium nitride (GaN) and silicon carbide (SiC) promise faster switching and lower energy loss. Photonic processors, which use light instead of electricity to transmit data, offer the potential for dramatically faster computation and communication with minimal heat generation. Three-dimensional (3D) chip stacking represents another frontier. By layering transistors vertically, engineers can dramatically increase density without enlarging the chip footprint. This design not only improves performance, but also reduces latency between components. Combined with innovations in cooling and thermal management, 3D architectures are redefining what is feasible in modern computing systems. 1.3 Memory and storage innovations. Hardware innovation extends beyond processors. Memory and storage systems are evolving at an equally rapid pace, driven by the need for speed, persistence, and energy efficiency. Emerging technologies like magnetoresistive RAM, MRAM, resistive RAM, ReRAM, and phase-change memory, PCM, offer non-volatile alternatives to traditional DRAM, combining the speed of volatile memory with the persistence of storage. These technologies are particularly critical for applications like AI training and real-time analytics, where vast amounts of data must be accessed and processed rapidly. On the storage front, innovations in NVMe-based SSDs and storage-class memory are reducing bottlenecks in data-intensive systems. Researchers are exploring new architectures where memory and storage converge, creating unified memory systems that minimize latency and maximize throughput.